A single train rail can stretch for more than 100 meters and weigh over 6,000 kilograms.
It is an enormous steel structure, built to withstand hundreds of tons of moving weight, extreme forces, and decades of continuous use. But here's the incredible part. That massive rail begins as raw iron. So how does ordinary iron become one of the strongest components of a modern railway?
We're going inside a giant rail manufacturing facility to uncover how these massive steel tracks are made for high-speed trains traveling at up to 350 kilometers per hour.
At those speeds, a high-speed train can weigh hundreds of tons, placing enormous forces on the rails beneath it.
One major challenge is the joints found in conventional railway tracks. Every time a train passes over a joint, its wheels create a small impact. At high speed, thousands of these repeated impacts can accelerate wear and damage the track.
That's why modern high-speed railways use extremely long, continuous rails and very gentle curves,
creating a smoother and more stable path for the train. But manufacturing a steel rail more than 100 meters long is an extraordinary industrial process.
The journey begins inside a steelmaking facility, with 3 basic ingredients: iron ore, coke, and limestone.
These materials are fed into a blast furnace, where temperatures can exceed 1,600 degrees Celsius.
The intense heat melts the iron ore, while coke helps remove oxygen and impurities.
Wine seal. The unwanted material combines with limestone to form slag, which separated from the heavier molten iron, the liquid iron,
where its chemical composition is carefully controlled. Carbon, manganese, and other elements are added to create the precise steel grade required for railway service.
The molten steel then enters a continuous casting system.
Inside water-cooled molds, the glowing metal begins to solidify into long rectangular sections known as billets. These red-hot billets are cut into manageable lengths before being transferred to a reheating furnace. There, they are heated to around 1,250 degrees Celsius, making the steel soft enough for the next stage.
But before rolling begins, the surface of the glowing billet is covered with a layer of oxide scale. Powerful, high-pressure water jets blast the surface, instantly turning into steam and stripping away the unwanted scale. Now, the clean, red-hot billet enters a series of enormous rolling mills.
Massive rollers squeeze and stretch the steel through multiple passes. With every pass, the billet becomes thinner, longer, and more precisely shaped. Slowly, the rectangular block transforms into the familiar railway profile.
With a wide base, a narrow central web, and a thick, rounded head. The steel continues to stretch until a single rail.
But the manufacturing process is still not complete. Identification markings are added to the hot steel, recording important information such as the manufacturer and rail specification. The rail is then cut to its required final length and enters a controlled cooling line. Here, its temperature is reduced gradually and precisely. This controlled cooling is critical. Uneven cooling could create internal stresses and weaken the rail. The part that comes into constant contact with train wheels. The result is a massive steel rail, engineered to withstand millions of wheel.
Once the rail leaves the controlled cooling system, there is still another problem to solve. It is not perfectly straight. To correct its shape, the rail enters a specialized straightening machine, equipped with 2 sets of large diameter rollers. The first set applies pressure vertically, pushing the steel upward and downward. The second works horizontally, forcing the rail from one side toward the other. The machine intentionally bends the rail beyond its natural curvature,
allowing the internal steel fibers to realign and bringing the entire rail back into a precise, straight line. But this requires extreme precision. Too little pressure, and the rail can spring back toward its original curve.
Laser sensors continuously measure the rail's deviation, allowing the system to automatically adjust the pressure applied by the rollers.
Once the rail is perfectly straight, its ends receive a final adjustment. before the finished rail leaves the factory.
In this facility, precision is paramount. Our automated systems utilize advanced laser technology to inspect every inch of steel rail,
while cameras and laser systems continuously examine its geometry. The equipment can detect deviations down to tenths of a millimeter.
Even a tiny variation can become a serious problem over thousands of kilometers, contributing to uneven wheel wear.
The steel is magnetized, and any discontinuity on its surface creates a change in the surrounding magnetic field.
These changes can reveal tiny cracks that are invisible to the naked eye. Critical defects result in rejection. There is no room for compromise. The safety of thousands of passengers depends on the structural integrity of every rail installed on the railway. But manufacturing the rail is only half the challenge. The next question is even more difficult. How do you transport a 120-meter-long steel rail,
weighing around 7 tons, from the factory to the railway, without damaging it?
The answer involves specialized cranes fitted with giant electromagnets. These powerful systems lift the rails while carefully controlling their movement.
The finished rails are then loaded onto ultra-long rail cars, positioned close together,
and protected with supports and shock absorbers to prevent movement and contact during transportation. Once the rails reach the railway, another remarkable machine takes over.
It is known as a track renewal train. Essentially, it is a complete railway construction factory mounted on wheels, stretching for hundreds of meters, and capable of performing multiple installation stages as it moves along the track. Modern track renewal machines can install between 500 and 2,000 meters of rail in a single day, a task that once required weeks of work and hundreds of workers. The machine moves slowly along the railway bed, while hydraulic arms position the massive steel rails.
Inside, automated systems transport concrete sleepers along conveyor belts. At the same time, rollers guide the rails into position and place them onto the support plates attached to the sleepers. As each rail reaches its correct position, automated units secure it with clips.
These clips hold the rail firmly while still allowing the controlled movement needed for thermal expansion as temperatures change. Next comes the tamping machine.
It uses vibrating rods that penetrate deep into the ballast beneath the sleepers. As the rods vibrate,
the stones shift and settle into their precise positions. The result is a stable, properly leveled foundation, with the exact alignment and inclination required for curves and high-speed operation. And after months of engineering, testing, and precision manufacturing, the enormous steel rail is finally ready to become part of a railway capable of carrying high-speed trains at hundreds of kilometers per hour. But there is still one final engineering challenge. If high-speed trains are going to travel at more than 300 kilometers per hour, smoothly and safely,
the rails cannot simply remain as separate sections, with noisy joints between them. Instead, individual rails are welded together to create one continuous railway line, extending for several kilometers. The welding process begins by placing a ceramic mold around the meeting point of two rails, leaving a small gap between their ends. Above the mold sits a crucible containing a mixture of aluminum powder and iron oxide. The mixture is ignited, triggering a chemical reaction
that reaches approximately 2,500 degrees Celsius within only a few seconds.
At that extreme temperature, molten steel is produced. The liquid steel flows into the ceramic mold, filling the gap between the two rails.
A grinding machine then removes and smooths the excess material from the surface. And that is how enormous steel rails are transformed into continuous railway lines, capable of carrying the incredible weight and speed of modern trains.
With smoothness, stability, and safety. If you enjoyed this journey, leave a like, share the video,